All right, tonight's lesson is about a couple of theorems that have to do with the angle sums of polygons. We call it the polygon angle sum theorems. We have one for the interior, sum of the interior angles of a polygon, and also for the exterior angles of a polygon. In addition, we're going to introduce parallelograms and talk about some properties of parallelograms that will help us as we go along and study quadrilaterals. So begin the lesson talking about a diagonal of a polygon. A segment that connects any two non-consecutive vertices is what a diagonal of a polygon is. If we look here in our drawing, I can't draw a segment here because those are consecutive vertices, but I can draw 1, 2, 3 from that particular point. And when I do that, it takes my hexagon here, which is a six-sided polygon, and it divides it into 1, 2, 3, 4 triangles. We already know that the measure of a triangle, sum of all its angles, is 180. So I have 180, 180, 180, 180, and 180 times 4 is 720. So the way we figure out the interior measure, sum of the measures of the angles of a polygon, is based off of triangles that we can create by the diagonals we can draw. So a six-sided figure, we can draw 3 diagonals. So there's 1, 2, 3, 4 triangles created. So 6 minus 2 gives us 4. 4 times 180. So that's what we're going to use for the... So we go to the next slide. Theorem 6.1, interior angle sum theorem. If a convex polygon has n sides and S is the sum of the measure of its interior angles, then S equals 180 times n minus 2. So in my picture here I have a pentagon. A pentagon has 5 sides, so n equals 5. So to figure out the measure of the sum of the measures of its interior angles, I do 180 times 5 minus 2, or 180 times 3, and it's 540. So this works for all in polygons, convex polygons. So let's continue on. That's the theorem. So let's say I have a hexagon here that we had earlier, which I showed you. I could draw 3 diagonals, created 4 triangles. So the sum of the measures of the interior angles of a hexagon equals 180 times n minus 2. So 6 minus 2 is 4. 180 times 4 gives us 720. So it's the simplest, it's easy as can be when we're talking about polygon angle sum theorem. Now the corollary to this theorem says that the measure of each interior angle of a regular n-gon is n minus 2 times 180 divided by n. So I take the sum of each of the interior angles and I divide by the number of sides that I have, which makes sense. It's the number of angles I have. So with a pentagon, as we showed earlier, n minus 2 times 180 divided by n. 5 minus 2 is 3. 3 times 540. 3 times 180 is 540. We divide by 5, so each angle of a pentagon is 108 degrees. All right, the sides of a polygon. The measure of the interior angle of a regular polygon is 108. So we can, from that, find the number of sides. So what we say is side equals 180 times n minus 2. So we're just basically doing the formula backwards. So we say 108n equals 180 times n minus 2. 108n equals 180n minus 360, the distributive property, and I get 360 equals 72n. Now I'll divide 360 by 72, and I get that the number of sides is 5. So basically I've just used both of those two theorems to figure out the number of sides that we have in a polygon based off of the interior angle measure. All right, in addition, we can talk about, so let's look at an example using interior angles, finding the measures of interior angles of a polygon. I have a quadrilateral, it's a trapezoid, and I know that the total measure of this quadrilateral is 360. I'm given the measure of angle A, B, C, and D, so I basically just add them up. X plus 2x plus 2x plus x. I get 6x when I do that. So the total measure of the quadrilateral is 360. 360 equals 6x, x equals 60. So the measure of my angles is angle A is 60, angle B is 120, angle C is 120, and angle D is 60. So that's basically how you find individual angles of a polygon. So if I had a pentagon, I know the pentagon's 540, and I'm giving different variables for each angle within the pentagon. I can add them up and set them equal to 540 and solve for x. Now the polygon exterior angle sum theorem, this is how we know that the total measure of the exterior angles of a polygon is 360. If a polygon is convex, then the sum of the measures of its exterior angles, one at each vertex, is 360 degrees. So I'm looking at my pentagon here. If I take angle 1, angle 2, 3, 4, and 5 and add them all together, they will equal 360 degrees. Now if I wanted to know which each one of those were, I could do it two ways. I've already decided that the interior angles of a convex pentagon are 108. So I could do 180 minus 108, or I could do 360 divided by 5, and that would give me 72. So each angle is 72 degrees. Each exterior angle of a pentagon is convex pentagon is 72 degrees. My apologies. Exterior angles. So now we want to find the measure of an exterior angle of an interior and an interior angle of a convex regular octagon A, B, C, D, E, F, G, H. Try to say that 10 times fast. So I know that it has 8 sides and 8 in equals 360 because I want to figure out each exterior angle. So it has 8 exterior angles. I divide 360 by 8 and I get 45. Now, to find the interior angle, at this point, to me, it's a lot easier just to say, well, the interior angle is supplementary with the exterior angle, so I can subtract 45 from 180, and I get that the interior angle of a convex regular octagon is 135 degrees. So that's what we talked about when we talk about the polygon angle sum theorems. We're going to do some worksheets in class tomorrow. If we have questions, we'll work over those questions that we have, and we'll review this tomorrow in class. A parallelogram is a quadrilateral with both pairs of opposite sides parallel. So here's my picture of my parallelogram. AB is parallel to DC, and AD is parallel to BC. The symbol you use for a parallelogram is that little symbol right there. Draw you one. Oops, maybe. So that's the symbol you use for parallelogram, and this is parallelogram ABCD. We have 4 basic properties and their theorems of parallelograms. They may seem like it's crazy, but they're not. It's just pretty basic. 6.3, opposite sides of parallelograms are congruent. So the opposite sides of a parallelogram are congruent. And in our drawing, AB is congruent to DC. And AD is congruent to BC. So that's theorem 6.3. Theorem 6.4. Consecutive angles in a parallelogram are supplementary. So angle A and angle B added together are 180. Angle B and angle C added together are 180. C and D, 180. A and D, 180. Okay, so this is just a basic fact property of a parallelogram. 6.5. Opposite angles in a parallelogram are congruent. So angle A is congruent to angle C, and angle D is congruent to angle B. Now, I got a lot of parallel lines going on here, and one of these parallel lines is basically going to be a transversal. So the way that we would prove this is angle A is a corresponding angle with the exterior angle of angle B, and angle B is, that exterior angle of angle B is an alternate interior angle with C. So therefore I have proven this theorem that A is congruent to C. In the same way, B is congruent to D. And then finally, if a quadrilateral is a parallelogram, then its diagonals bisect each other. So here's my quadrilateral. It's a parallelogram. So AE is congruent to EC, and BE is congruent to BD. Additional properties of parallelograms. So this is solving problems with these properties. Quadrilateral LNMP is a parallelogram. I want to find the measure of PLM, the measure of LMN, and I want to find the value of D. That side is 2D. So the first thing I'm going to use is 6.5. Remember that 6.5 said that opposite angles of parallelograms are congruent. So PLM is equal to 42 plus 66. I just use the angle addition postulate. 42 plus 66 is 108. So PLM is equal to 108. Now for the next one, I use the fact that in parallelograms that consecutive side angles are supplementary. So PLM plus LMN equal 180. I've already said that PLM equals 108, so I subtract 108 from 180, and I know that LMN equals 72. So this angle is 72. And then finally, I know that opposite sides of parallelograms are congruent. So 2D equals 22, and I put D in for 11. Of course, this side is 22 also. We're going to talk about Theorem 6.7. If 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So here's what we're saying. I've got 3 lines that are parallel. I've got A, C, and E. All these lines are parallel, A, B, C, D, E, F. And AC is congruent to CE. So therefore, we know that BD okay, let's try that again. BD is congruent to DF. All right, I know it's a lot of theorems that we went over today. Your best bet is when you're watching a video is to pause it. If you need to go back and watch again, pause it, write down the theorems on your theorem sheets, and we'll go over some worksheets in class to make sure we understand these. It's some basic concepts dealing with parallelograms and with polygons, and should be able to knock this out tomorrow in class. It's not a real big deal, so you have the weekend to work on your kite project. All right, so see everybody tomorrow. Hope you have a good evening.